Hi, I want to talk about system I/O today. This is necessary in order to do network programming via sockets. You'll use the system I/O routines to do that. It's useful actually for a number of different applications as well. You can always do I/O at the system level instead of using higher level language routines. There is an exercise corresponding to today's lecture. It's fairly simple. I'll talk about that briefly at the end of the lecture today, but make sure you go through that exercise because it will prepare you for the next project, which is assigned today. The project is pretty simple. It's not networking yet. It's actually just using some of the system I/O routines um, to get data from various data structures in the operating system and then write those to the serial terminal. Okay, so let's get started. So the network communication facilities, the socket routines use the NetBurner system I/O routines. These are known as read and write. And you may have run into these before if you've taken any sort of Unix programming class. They are the POSIX, mostly POSIX compatible routines. And it's useful to get to know them, become familiar with them, because they're used by almost all real-time operating systems at the system level, and also by well, all Unix operating systems. The system I/O routines can be used for doing I/O on the console or serial terminal. Also writing across the network, doing network communication via sockets, and also for serial port I/O. Unix systems have long had this philosophy to try and treat everything as a file. So even serial I/O devices, to treat them just like you would a file. You're able to read and write from them using the same routines. Read and write. Now that not only simplifies things for the programmer, you just have to get to know these two routines, read and write, in order to do lots of different file types of I/O. I/O to files, I/O to terminals, I/O to serial ports, I/O across networks. All use the same routines. These routines in Unix, read and write. In addition to that, from a user standpoint, an application then that reads to a file can have its output or input redirected, or if it writes to a file, you can redirect its output. So it goes to, perhaps a sound card and plays music, or you can capture input from a microphone directly into a file, or read directly from the microphone, or again write out to a serial port, or even write across a network. So it's a very flexible and powerful I/O paradigm. So the open, read, write, and close routines are the only routines provided by the operating system for doing I/O. Again, this is true, for POSIX compatible systems. Programming languages provide their own higher level routines. So in C, it's the printf and scanf that we've been using. Those are part of the standard C library. And in C++, you also have the C++ streams. Again, those are all higher level language facilities built on top of the lower level system I/O routines. Ultimately, printf calls write, underneath the covers at a lower level in order to write data to standard output. Okay. Now the system I/O routines use file descriptors. Now these are not the same as the file star pointers that you're used to using in C. File descriptor is just it's an integer. The integer is associated with a particular communication stream. Typically on POSIX compatible systems, you call open, and then the open routine returns a file descriptor, this integer value that you then use in your read and write routines to do I/O. NetBurner instead of having open, it uses connect and then also open serial to return file descriptors. We'll be using connect when we start doing network I/O. Now, the good news is standard input, standard output, and standard error are available automatically and correspond to file descriptors 0, 1, and 2. So file descriptor 0 is input, so you can read from that. That would correspond actually to your keyboard. Okay, by default, when MTTY is open, all of these are redirected across our serial communication link. So with MTTY open, reading from descriptor 0 would essentially read data from the keyboard. File descriptors 1 and 2 are both output, so you can write to those. Any data written to 1 and 2 would be sent to our serial console or our MTTY console. Okay. First we'll talk about write. The write function writes data to the stream associated with a file descriptor. So the arguments are the file descriptor, and if we want to write to the terminal with standard output, that's just the integer 1. Then next comes a pointer to the area of memory that we want to write out to that particular data stream, and then the number of bytes from that memory location. Okay, so the number of bytes actually written then is returned. There's no guarantee actually that the number of bytes that you request to be written are actually written in a single write. And I'll talk more about that in just a second. The issue there is that not all streams can handle arbitrarily large number of bytes, and so the operating system may actually break your single write up into write a smaller number of bytes than you request. You get a negative number back if an error occurs. Okay, so the other thing here to keep in mind is writes binary data. It doesn't do binary to ASCII conversion like printf or the cout stream. If you write ASCII data, then it's sent directly to the terminal, and then the terminal will display that as ASCII characters as you expect. But printf, if you write an integer out using the %d format specifier, that integer is converted to a decimal representation that's displayed on the terminal. And if you pass the integer value, a pointer to the integer value, and write that number of bytes out to the terminal, it sends that binary data to the terminal, and it won't be displayed properly. If you wanted to display it as a corresponding in its corresponding ASCII decimal representation, you have to do that conversion. And an easy way to do that is to use sprintf to actually convert the binary to an ASCII array, a char array, and then write the char array to the terminal. The write call will block until at least 1 byte is written. It does not have to block until all requested bytes have been written. So you have to look at the return value and then keep retrying to write the data that you're trying to send across until all the data has been written. Okay, so here's one method to do that, where our message ultimately consists of 10 bytes in the message. So we initially, and then n is equal to 0. So pointer here is a pointer to the start of memory that we want to write out 10 bytes to this particular file descriptor. So initially n is 0, and so this points to the beginning of the buffer, and then we're initially again requesting 10 bytes be written. If n is less than 0, that means that an error occurred and we break out, and then we would check the status of n. If n is not less than or equal to 0, we want to go back and see if it's equal to 10 bytes. If it's equal to n bytes, 10 bytes in this case, we're done and we drop out of the while loop. If it's not, if it's less than 10, then we want to write out the remaining bytes. Let's say this initial write only writes out 6 bytes, then we subtract 6 from 10, and so now we're going to try and write the remaining 4 bytes, and then the pointer now would point past the first 6 bytes, which have already been written, and then point to the last 4 bytes. So something like this is the mechanism that should be used when you're trying to write data via the write system call. Now, having said that, a lot of programmers will assume that for small messages, write will write the entire data block in with just one write command, but that's not recommended programming practice. So this is a recommended approach. Okay. So here's some examples. Again, I haven't, I'm not following the approach on the previous page where I'm actually checking to see in each case that all of the data has been written, but it's just too many slides if I do all of that checking. But so here I'm assuming that the data is written in a single write. So here's how I could write an ASCII stream. In this case, it would appear on my terminal, on my serial terminal, because I'm writing to file descriptor 1. str is a pointer to the beginning of the string, and string length string then would be the number of bytes. In this case, 5, 6, 7, 8, 9, 10, 11, 12, 13 bytes, including this new line character. And the new line is actually sent to the terminal as well. And so there is a trailing 0 that's part of the string, but that's not included in the string length. Now, I could include that. That trailing 0 is not typically sent to the terminal by printf, and so I'm not doing that here. But there are reasons if I'm doing inter-process communication, writing data to another task, I may want to include that 0 as a terminator, or maybe just look for the new line as a terminator to know that I've got the entire message. Now, if I want to do write a binary number across, I just pass a pointer to that particular number. In this case, size of int would be 4 bytes. This is 1, 2, 3, 4, 5 is the decimal representation, but that's much less than the 4 billion, which we can, well, I guess this is a signed int, so the signed int values can hold between -2 and +2 billion approximately. So size of int would be 4 bytes, and then this would write the corresponding binary representation of this number across the stream. Now, this would cause, not random characters, but whatever the corresponding ASCII characters are corresponding to those 4 binary bytes to be displayed on my terminal. So normally you wouldn't do this for terminal I/O, right? You might write something like this to another process or to a file if you're doing binary output to a file, but you typically wouldn't send raw binary like this to a terminal. Instead, what you would typically do is convert the number to ASCII, and again, we can do that with sprintf. So here I'm going to convert that 4-byte binary number back to its decimal representation. In this case, it would be 1, 2, 3, 4, 5, and then add a new line to it. That would all be in string, and then now I can send that string across to my terminal. String length here would actually be the number of ASCII characters, 5 plus the new line, so string length of string would be 6, and then now this number would then appear on the terminal. Okay. Read, same number of arguments. The file descriptor we want to read from. Again, this would be 0 for us right now if we're reading from the terminal. Ultimately we'll be reading from a connected socket for file I/O. This is a pointer to an area of memory. You have to have allocated space. Okay, read won't allocate this memory space for you, so you have to allocate space. So this could be, the start of an array. It has to be large enough to hold the number of the number of bytes you want to read, and then n bytes is actually the number of bytes that you want to read. You need to make sure that that's smaller than, equal to or smaller than the amount of memory you set aside here. Again, you don't really know how many bytes are being sent across. I'll talk a little bit more about that later. Often you'll use a terminator, or maybe when you're writing data across, you'll precede the message with the number of bytes that are to be written. So on the reader side, you'll first read that integer which contains the number of bytes, and then keep reading until you've read the entire message in. Okay. The number of bytes actually read is returned. Here that will generally be less than n bytes. Again, it depends on the number of bytes that are being sent across, unless you're reading from a file. But even when you get to the end of the file, it'll just read the number of bytes remaining. It won't read past the file, and it will return the number of bytes actually read. A negative number indicates that an error occurred, and you should check for that. Okay. Again, reads binary data. It doesn't convert numbers from ASCII like scanf does. Read will block until at least one byte is read. It doesn't have to block until all the bytes that you've requested have been read. You have to confirm, look at the return value, and keep reading the data until you've got the entire message. Again, that's a little bit tricky. How do you determine when you've read the entire message? So here's a couple of examples. I've allocated 100 bytes here. And then now I'm calling read to read in 99 bytes and store it in string. And then I'm actually terminating the string with a null byte, a binary 0 byte. Now notice how this is done. Let's say only 10 bytes are read in, then n will be 10. And the data bytes will actually be stored in string 0 through 9. And I set string 10 equal to 0 to null terminate the string. Now here I'm assuming that the 0 wasn't sent across as part of the message, okay? And so I have to properly terminate the string. If the 0 was written as part of the string, then that would be included in the number of bytes read, and the string would already be properly terminated. I mean, that's up to you as the application developer, what kind of communication format you want to use for passing this data between processes. So this would be for reading, ASCII formatted data. If I'm reading a binary number, I know that I have to know what's in the stream, whether it's a number coming across, whether it's a float or double. I could pass all of that stuff, although passing floating point, binary floating point has its own pitfalls. But it's relatively safe to pass integer data back and forth. Almost all computer architectures use the same representation for ints. We still do have the Indian issue that you might run into if you're passing data between different architectures, little Indian and big Indian. But here's how you'd pass a binary number, or read in a binary number. Again, I show reading from 0 here. Typically, you wouldn't read from standard input here. I'm assuming that standard input has been redirected, so you're actually reading from a socket or a file. Okay. This is the last slide. Again, using read or write for file I/O is fairly straightforward. Just keep in mind it doesn't do conversion to ASCII for you, or conversion from ASCII to binary for you, like printf and scanf. You have to do that. The trick here is, with the writing task, you need to let the other task that's going to read the data how long the message is. And again, there have been a number of different data encoding methods that have been developed, but two simple ones are, to determine the size on the writing task, determine the size of the message that you want to send across. Say maybe it's 200 bytes. Then the first thing you would do is send a binary 200 across to the reading task, followed immediately by the message. So the reading task immediately knows that it's going to read first an int, and then it would read that int value in. That would be the integer 200, and then it would continue to call read until it's read 200, the next 200 bytes into an array somewhere. And then after it's read the 200 bytes, it'll prepare to read the next integer, which would then be the length of the next message. Another technique that's used is to actually terminate the message with a special termination byte or bytes. A null byte could be used to indicate that not only the end of a string, but the end of a write that's sending a string across the data stream. You have to take sure that termination byte doesn't appear anywhere in the message. Because if it does, when the reading task gets to that, it's going to think that that's the end of the message when it's really not. So again, there's some various techniques that have been developed to deal with that situation. Okay, let's take a look at here's the in-class exercise today. This is fairly simple. You might think it's so simple you don't need to do it, but don't make that assumption. It's just a few lines of code, but do this exercise. It will help you make a lot of progress towards the next project. Okay, so create a new project in NB Eclipse that first displays a prompt on the serial terminal, and the prompt I'm suggesting is just a greater than sign and then a space. And you're going to use the write command to display that prompt. The program should then read any text entered by the user. So in this example, the prompt is displayed. The user has entered hello world. You're going to use read then to read this message from the terminal. Now the way the terminal program works, you're really doing inter-process communication here between the net burner task and then the process running on your computer that's running the terminal. But the MTTY terminal actually doesn't send a message across until the user presses enter. And then that's when this entire message would be sent across the serial link. This entire message, the net burner is going to read that in and then display it back, echo it back to the terminal, and then present another prompt. And then it would just continue to do this forever. Now I put a note here. I don't think you'll have to do this. I mean, you will have to have the right type of string termination. Either carriage return, which the C string encoding for that is a \r, or a new line \n. I think most of you are familiar with in C. Typically, you just use a \n to terminate a string. Again, whether you do that from at the net burner side, add it here, or you do it well, actually you're only writing the one task, so you may have to include new line characters or returns after or before each string that you send across so that it appears like this. So again, not a lot of code here. I do encourage you to, even though we're using the serial connector here, use the enable update routine that we talked about last time so that you can at least load your program over the Ethernet link on your computer. It's not required here because we're not actually doing, you're not using the network for communication just yet, but it's so much faster than downloading your program over the serial link. Again, you will need to have both the Ethernet um, connector connected to your computer, as well as well as the serial link. Again, this particular exercise, you could do it just using the serial connector, but I'm encouraging you to get used to transferring the program over the Ethernet connector. Our next project will actually be, I'll have you doing network communication using the sockets API. Okay, so let's look at this next project too. Again, it's fairly simple. It's actually just doing using read and write. You're going to write a NetBurner application that displays this menu. The user then types in a particular number, the maximum number of tasks, the MAC address, the net mask, and then your program would read in that number and then display the corresponding item, and then go back and display the menu again. Okay. Now, part of this is the net mask, gateway IP, and IP address should all be shown in dotted quad notation, not in the binary format that you'll find. And the bytes that make up the 48-bit MAC address should be shown in hexadecimal. So there's a bit of data formatting here that you'll have to do. You're only allowed to use the read and write routines for input and output. You can't use scanf or printf or any of this. You can use any of the routines in the NetBurner runtime library. There are some convenience functions like show MAC or show IP, but you're not allowed to use those either. You have to do all of the formatting of that. Now, where do you find all this information? Look in the documentation. You'll find the location for all of this stuff. They're either defined in various header constants, or they're defined in a particular structure that's defined in this section of the runtime library. So you'll be able to get these corresponding entries out of that structure and then display them to across the serial link to the MTTY terminal. And then submit your source code via the submission system as you've done in the past. This project is due a week from Thursday. Okay, there is no class on Thursday due to our Easter holiday break. So I won't have your next lecture where we'll start talking about sockets program until next Tuesday. So you got a lot of time to work on this project. Don't put it off, because I know some of you are actually going to struggle with just some of the fundamentals of reading and writing and getting this data out of the structure and then formatting it appropriately. Yeah, it's trivial once you've done it, but until you've done it, it can be a bit tricky. So don't put this project off too long. Okay, that's it for today's lecture. We've been normally meeting on Thursday for our Zoom meeting. Again, we won't have that this week because of our Easter break. I think you should have gotten an email message that I am having office hours on Monday, Wednesday, and Friday in the morning, I think at 9 o'clock. So if you have any questions, you can contact me on Monday, Wednesday, or Friday during my office hours. I won't be having office hours this Friday because of the holiday, but you can contact me either tomorrow, Wednesday, or next Monday. So.